This is the A100 construction details page on the Derpfer website. Dieter Derpfer originally came up with the specification for Eurorack, and in here he specifies that all panels should be a multiple of 1 HP wide, and 1 HP is 5.08 millimeters, and they should be 128.5 mil high. Now I'm going to try and fit all this in a 12 HP panel, and so theoretically the panel should be 60.96, that's 12 times 5.08, 60.96 mil wide. But he says you shouldn't make the panels exactly that width. You need a little bit of tolerance, and so the suggested width for a 12 HP panel is 60.6 by 128.5. Now the circuit board needs to fit behind that. It can't be the entire height because you've got the mounting rails at the top, and it seems that a usable height for a PCB maximum height is about 110 mil. Width-wise, I don't want my PCB to be the entire width. I need, again, a little bit of tolerance, and so I'm going to leave a millimeter each side. So my PCB ends up being 58.6 wide by 110 mil high. Back in KiCad in the PCB editor, I'm going to make the circuit board as actually one large circuit board with a V-score down the middle so that it can be snapped apart and the two halves of the board fit back to back. So I've drawn my board outline as being 110 mil high by 2 times 58.6, so that's 117.2 millimeters wide, so 110 by 117 wide. And I've put my board origin here at a nice convenient point. That's 30 by 30, so I'm using that as my board origin, and all the placing of components is going to be relative to that board position. The first thing I need to do is put my V-score in, which is going to be the line between the two boards where it can snap apart. So I'm going to put this on the user Eco 1 layer, so I select the line tool, and it's going to be at 58.6 mil across, and because my board origin is 30, it's going to be at 88 mil across. So I find 88.6 mil across. So that's from there, and we go down to the bottom and find 88.6 mil across, which is for 88.6 there. Zoom in a bit, get it accurate. 88.6, poof, there. Okay, so that's my V-score. Next, and this is where the fun starts, we need to import all our footprints from the PCB. So to do that, you use the Update PCB from Schematic or the F8 shortcut. It reassigns all the footprints, update the PCB, close, and there we are. We've got all our footprints, and I'll just stick them over the side at the moment. And they're all connected up with a mass of air wires. So the fun of PCB design is to replace each of these little light blue air wires with a real trace, a real copper trace. But before that, I've got to work out how I'm going to place all of these components so that they make sense. I've sketched out what I think might work as a front panel layout. So I've drawn my 128.5 by 60.6 is the panel width, and then my circuit board is 58.6 by 110, and I've laid out the components as I think makes sense. So I've got feedback, wet dry balance, I've got my delay time, the rotary encoder, I've got switches for algorithm selection, and my multiplication division ratio, that kind of thing. And I've measured and laid them out so that they're nicely balanced and positioned on a vertical and horizontal grid, and so that gives me coordinate locations for each of the center points of the components. back in the PCB editor, I'm going to place the feedback pot. That's the first one, top left hand corner, and that's RV4, so click somewhere in it, and then if I select E for, or press E for edit, it brings up some details about it, and I can key in the coordinates, and I know that the coordinates from my grid are that needs to go on 43 by 36. Click go, and there it is. And remember that R is for rotate. There we are. And then all I need to do is place the remaining components on my grid. And finally my two little two-way switches. So that's at 77.6 by 94.2, and this one is at 41 by 94.2, and there we are. So that's the front panel components, all positioned, I think. Next up are the major components on the other half of the board. So start with the Pico. Now I'm going to slot my pin headers in between the other components. I've left space to so that they will marry up, and this is where I've had to measure relative distances very accurately. And finally J15, which will go at 91.6 by 36.5. Bang. And there we are. So those are all the major components placed on the two halves of the board. And finally I need to place the other remaining components somewhere near where they're going to go. So if I pick up this, which is the MC14532, I can see from the air wires that it needs to be pretty close to this SW5, and by rotating it I can see how tangled up those wires are, and the answer is always. However, I can flip it onto the back of the circuit board and put it on the back copper layer, for which you just press F, and it's now on the back. You can see the writings upside down, and I can try it round there, and I can see that if I put it like that, where it will just go in between these two switches, none of the air wires are really tangled up, so that's a very good place for it to go. And I won't bore you with all the rest, but I need to place all the rest of the components either on the front or the back, close to where the air wires dictate they ought to end up. I think that's about it. I've got all the components placed on the board. I've tried wherever possible to reduce the tangles on the air wires, the rat's nest. Some of the components are on the front, some are on the back. And if I look at the 3D viewer, we can see what the board currently looks like. And yeah, I think that looks okay. If I flip it over, you can see the male and female pin headers that will join the two sections of the board together. I've got these are the I/O driver circuits, the op amps, and yeah, I think that's going to work. And the 3D footprints for the two modules that we made up earlier. But all that remains now is to route all of these traces, and for that you need to watch the next episode.